Okay, we're recording now. Sorry. So we're looking through number 4. We're looking at what we have set up so far. I'll just say that I was just commenting on how great how great it was that when you guys were working on this, you figured out that the radius of the original circle is the hypotenuse of this triangle on the cone. So that gave us access to Pythagorean theorem, which is basically a constraint. This is our constraint. It's like a constraint equation. It's related to the constraint. This was labeled constraint over here as well, which is true. But I think that gives us access to this equation. So now, we've got some interesting things happening over here where we tried setting up the volume as a function of R on the one hand. On the left over here, this was setting up volume as a function of R. But I think now what we're trying on the right side here is setting up volume as a function of H, which I think ends up being a little easier because it doesn't involve that square root. It's just a like basically a polynomial, which is nice. So I think I like the look of that. I think it's just going to make the derivative easier. And there it is, v prime. Much easier to do. So now the problem is, actually, maybe there isn't a problem. What are you guys going to do next?
I think we should find the h fast for that, like when it's 0 and find h, and then plug it back to in our equation for r squared is equals to h squared minus 144. Find our r squared. So we have r, the value of r and h, and then we find theta up there, like the angle between the height and the hypotenuse. And then we square it to find our theta. Oh, times 2, sorry, not square it.
There's going to be something, well, somehow once you figure out the R or the H, whichever one you figure out. So you're doing the optimization, you're not even doing the optimization with theta. You're doing the optimization with either H or R, right? So yeah, you're going to optimize the volume, you're going to figure out the H. If you need to figure out R, you can go the corresponding R value. You can go back to the Pythagorean theorem. But yeah, as Julia was saying, somehow you need to relate it back to theta. And that part remains a little bit, I didn't quite follow what you were suggesting with relating it back to theta.
I think theta is the angle made between the hypotenuse, the 12 inches with the h, but you gotta times 2 to get the whole theta.
Oh, you mean this angle here?
And then the other side also. The other side of h, like the whole thing, yeah. That's the angle we're looking for, I think.
That's not quite the same angle. Yeah, it's not the same angle. If you make this angle very small, if you make theta very small, then when you form the cone, you actually have a very wide cone. So if this theta is very small, then this angle is big. And vice versa. If you make a very large theta, then you have a small wedge of circle, which when you roll it up to make a cone is going to give you a very skinny cone like this. And you have a very small. So a large theta corresponds to a small angle at the top of the cone. So those two angles can't be equal because they are in some sort of inverse proportion to each other. I'm going to leave that question of how exactly we relate our R or H value that we get from the optimization back to theta. I'm going to leave that hanging a little bit and let you think about that. It's not really relevant to the optimization topic, right? It's more so like a geometry problem, right? Yeah. The actual optimization is going great. You guys are killing it here with the optimization. So that is looking good. It looks like we pretty much got, h equals 12. No, h can't equal 12. H equals 12 would be a problem because if h is equal to 12, the hypotenuse and the h would be the same value. And then what you would have is a cone of 0 volume, which might be the minimum. Maybe this is the wrong, this might be the wrong critical number. Maybe this is a critical number, but there's another critical number. Okay, I'm going to move on from this one. Sorry, go ahead.
I found my h to be the square root of 48. I don't know what happened in the calculation there, but h was the square root of 48.
Okay, I'll write that here, square root of 48 maybe. So you guys can see if you can identify whatever. Oh, hey, here it is. Yeah, look, square root of 48. Lovely. Okay, just a little arithmetic error there. Okay, so we got 2 votes for square root of 48, so that's probably right. Let's look at the next one. So the next one here, we have this sort of box-shaped thing. I have been calling one of these triangles the base of the box, and then the rectangles would be like the sides of the box. So I drew it basically on its side, which is just because it was easier to draw that way. But anyway, so how are we doing here? We have the volume. The volume is the area of a triangle, which I gave you a formula for, right? Times the height. So that is great. The area here was this term, this first term, square root of 3 over 2 s squared. You'll notice the original area is square root of 3 over 4 s squared. So why does it change from 4 to 2? What are we doing here?
They might have square rooted the 4 by mistake.
Oh, I wasn't trying to make a correction. What was written there was correct. It is supposed to be square root of 3 over 2, but I just wanted you guys to explain why. How many triangles are there that you have to add up when you calculate the area, the surface area?
2.
Yeah, there's 2 triangles. So if they're the same size, you can just do triangle plus triangle is 2 times the triangle, right? So like square root of 3 over 4 s squared times 2, because there's 2 of them. So that's why it's a 2 in the denominator instead of a 4. It's because you multiplied it by 2 because there were 2 sides of that area that you needed to add together. Now, speaking of adding, I came in here earlier and made this correction. I think this was originally written as multiplying. This is adding. When you're calculating volume, generally you do things like multiply different dimensions together, right? Or like this area times that height, you multiply, right? But when you're calculating surface area, is more about just adding up the different areas of all the different faces, surface faces of the shape. So yeah, got 2 triangles and 3 rectangles, and we are adding them together. Yeah, and then, yeah, yes, nice. This is basically going to serve as our constraint. We can solve this for either S or H, and then substitute into our volume equation, which is the volume is the actual thing we want to optimize. Do we know the or wait, actually, let me take that back. I forgot. Actually, it's the other way around. Yes, there someone is you guys are right with me. We're on the same page. We made the same mistake and we've realized our mistakes. So yes, actually the way this is written, we want to minimize. Yeah, man, we are like so on the same wavelength. Look at us underlining the same part of the thing. Yeah, we want to minimize that surface area. So actually it's other way around. Now solving the volume for S or H or whatever isn't going to help very much if we still have a volume variable over here. So do we actually, are we given something? Oh yeah, check it out. Volume wants to be exactly 1 cubic foot. So actually we can get right in there to the volume and we can replace that V with a 1. And then we don't have a V variable, like V variable is gone. We just got a 1. We can solve for H or S. Do you guys want to solve for H or S? Technically, you can do it either way. If you solve for S, you have to take a square root. Julia?
I'll take the H.
Yeah, let's solve for H. Then we don't have to deal with a square root, right? So that seems a little easier. And then we substitute in for this H over here. So that H, this H over here is going to get replaced. Maybe I can do a, oh no, that's too big. This guy, yeah. We're going to substitute in for that H right there when we're done. That guy's going in here. And then we'll have an area formula to work with. And the area will then be a function of one variable, which is the S, the side of the triangle. And so from there, you can then, do your derivative, find your critical numbers, do the derivative testing to figure out if it's a max or a min. You're off to the races at that point. So that looks great. Let's move on to the next one. All right, so this was looking pretty good. We got a really good start on this problem. So this problem is tricky. Let me zoom in on this guy here. So we have this length, this total length here that we're trying to study. Are we trying to minimize or maximize on this problem, by the way? Great. So so Hannah, were you working on this one over here? This is some, so you guys worked with Braden yesterday? Excellent. Yes, Braden would remember this one. We worked on this one last semester. Yeah, we've got this length here, L. Are we trying to like minimize that or maximize this? What are we trying to do with that? It says we want to find the length of the longest item, which can be carried horizontally around the corner. So that the word longest sounds like maximizing. Yeah, the word longest makes it sound like maximizing, but Hannah, you're saying you've looked at the graph of like after you get like so after we get something going on over here, you've looked at a graph and the graph makes it look like we want to minimize it. Yes, it does. So yeah, so in fact, what we do want to do is minimize, and I'll draw a little picture to explain why. Okay, so here's our situation with the 8 feet and a 6 feet here, right? Different possible lengths. There's a length like this, right? Okay, so here's the thing. If you're carrying a long object down this hall and you're going to get around the corner, you might as well carry it such that it like touches that corner. Okay, because you're going to get the maximum amount of like length if you sort of pivot around that corner, maybe slide along the corner, right? I'm just kind of trying to actually imagine. I've done a lot of moving in my life. I've like moved apartments many times and carried things around apartment buildings and stuff. And yeah, so I'm just kind of speaking from like just intuitive experience kind of thing. You want to slide around that corner. So that's why this thing is drawn like that. Okay, that's why it's sort of drawn through that point. But then there's different possible distances through that point. Okay. Okay. We have some long ones, like this here is quite long. This one is quite long. But then somewhere in here, we have a minimum. The thing is, if you are going to get a long object around the corner, it has to be able to fit through all of these distances, all of these gaps, right? So the smallest gap is the length of the longest item that you can carry around the corner, right? If the item were any longer, it wouldn't be able to fit in that smallest gap, and therefore it would get stuck. Does that make sense? So actually, this is a minimizing optimization problem, not a maximizing optimization problem, despite the wording longest item, okay? Because we're not really calculating the length of the item, we're calculating the length of the gap that the item has to fit through. Yeah, so there we go. So now the way we have it set up here, this is very nice. We have an A and a B and an L. So overall, the A and the B and the L form a right triangle. Here is a right angle. So we have basically Pythagorean theorem with A, B, and L. That's a great start. Then we have, how does the 8 come into play? Well, the A is going to be like 8 plus a bit. So the way this is labeled here, we have this extra amount here, the distance out to this point. That's Y. So A is 8 plus this Y amount. And then B is the 6 plus this X amount. And the X amount would therefore be, right there, that amount. So that's cool. So now we have some variables to work with. We're not actually going to be using A and B as our variables. Those were just temporary. Now we're using A is 8 plus Y and B is 6 plus X. But then the real key constraint here comes from this idea of similar triangles. So this was my hint here, is to draw these two little blue triangles. Those are similar to each other. And that gives us a relationship. We have, an X to 8 ratio is the same as the 6 to Y ratio. And then that allows us to solve for X, substitute back in, and get that L as a function of one variable there. Okay. So we're out of time. That's it. You guys did a great job. We are more or less on schedule. If you want, we can spend a little more time tomorrow talking about optimization, but we should wrap that up and be done with optimization so that we can move on to our next topic before the end of this week. Okay. What do you guys think? Just a little feedback from you now. Do you think we should spend a little more time on optimization tomorrow? Yeah? I'm seeing some yeses. Okay. Well, think about it. You can let me know tomorrow if you want. Okay, folks. Have a good one.